Good morning. All right. Next Tuesday, we're not going to meet in person. That lecture is going to be online only. And if you look at the course schedule, we had a quiz scheduled for that day. And so what it means is you're going to have a temporary 48-hour reprieve on that quiz. It'll be pushed to Thursday, the 18th of April, instead of being on the 16th. And you may remember or already know that when I have an online class, I like to check up and see who's watched that. And so the fact that you've got a quiz immediately after an online class, I hope, is a little bit of added incentive to slog your way through that video. All right? So also on Tuesday, homework 13 is due, and that's related to hydraulic jumps, which we started on in last class period and we're going to continue talking about today. And that assignment also has a couple of problems related to underflow gates. All right, so any questions related to the announcements? I hope that we're going to be able to spring through this assignment pretty quickly and get a chance to go down into the lab and observe a couple of hydraulic jumps. So that is the plan. We'll hopefully have about 10 minutes to go down there and look at some things at the end of the lecture. All right, so last time what we saw was the Bellinger momentum equation, which predicts the downstream depth of a hydraulic jump on the basis of how supercritical is the flow upstream. You know, this Froude number is a representation essentially of how far away from the critical condition you are upstream. So you'll notice this is FR at 1, meaning before the jump. And so it predicts the conjugate depth, sometimes also called the sequent depth, meaning the depth with the same amount of momentum. All right, so on this momentum depth diagram that I put up on the screen, let's just assume that we have a certain flow condition that yields us this momentum depth diagram. So with this figure, what is the critical depth approximately for the momentum depth diagram that's shown? Maybe this would be a good proxy for your quiz readiness. Would you be able to pick off the critical depth from this figure? Hopefully you would, because there's only one unique point on that figure. There's only one point where, I don't know, something specific is happening. So the point furthest to the left, it looks like that would be associated with a depth of about, let's see, 0.5, 6, 7, about 0.8 meters, I'd say, is approximately the critical depth. All right, now, how do we use the momentum depth diagram if we want to predict the conjugate depth? Let's say that we had a known upstream depth before the jump of 0.6 meters. So here's the 0.6 meter. What is the Y2? So just kind of maybe if you have a I guess you'd need a telescope, not a microscope. A telescope to zoom in really easily. Basically, it's connecting the momentum depth diagram with a vertical line. So 0.6 is the upstream depth before the jump. And so the amount of depth that has the same momentum, it looks like that's approximately, so let's see, 1.05 roughly. So 1.05. So that's a relatively small jump. The length of this line represents the elevation difference between upstream and downstream depth. So this orange line goes from 0.6 to 1.05, so that gives you the height of the jump. Now, the Y1 in this first illustration was pretty close to the critical depth. If critical depth was 0.8 and the Y1 that we're talking about is 0.6, then what we can think of is that that's barely supercritical flow. Like, remember that the region below the critical depth is the supercritical region of a momentum depth diagram, and the region above the critical depth, that's the subcritical region. So if the flow depth is 0.6, then the Froude number probably wouldn't be very high because the two depths are relatively close together. So the jump height is small, and we could say that it's barely supercritical. Now think about now, what if the y1 was 0.3? So now we're quite a bit further away from the critical depth. And so now flow conditions are going to be more supercritical. The Froude number would be much higher for that kind of a depth. To find the y2, we'd again just connect the lower momentum amount. And so it looks like if we have a depth of 0.3, then we're talking about 12 cubic meters of momentum. And we go back up to the conjugate that has that same amount of momentum. It looks like now we're talking at a downstream depth of 1.5, 1.6, 1.75. And so it went from 0.3 to 1.75. That's a big jump. And in a big jump like that, you're going to be losing quite a lot of energy. And that may be the objective, to dissipate energy so that there isn't a bunch of hydraulic scour in the channel downstream. So the lesson is that if the y1 and yc are far apart, that's going to set up a very vigorous, distinctive jump where there's a lot more energy loss because you're starting with the higher Froude number. Do these trends make sense to everybody? The interpretation of the diagram, how to find the depths, more supercritical versus barely supercritical? Yeah?
Is the length of your green line, would that be the height of the hydraulic jump?
Yeah. So what that line length, this green line, would be the difference in elevation between y1 and y2. So if I extended a horizontal line from y2 and then I measured down to the water surface, that's the height of the jump, the difference in elevations. Sometimes you'll barely even see the difference in elevation. In an undular jump, where the Froude number is just barely above 1, you may not even notice that you're having a hydraulic jump because these very gentle surface undulations look almost indistinguishable from just the ripples that you'd ordinarily experience from maybe having gravel at the bottom of a channel, or even down in the flume where it's a relatively smooth channel. You'll still just see surface undulations that are having to do with maybe minor variations in flow rate on the pump or turbulence when the water is changing directions. So the point is that when you have a relatively low Froude number, so above 1, meaning it's supercritical, but not very far above 1, then all you end up with is a slightly ruffled water surface, and you're hardly losing any energy at all. A weak jump, things start to get a little bit more interesting, and usually in the range of 1.7 to 2.5 for the Froude number is what's characterized with the weak jump. And now finally, the ratio in the upstream and downstream depth is starting to get a little bit interesting. You can visually tell that there's a hydraulic jump if the downstream depth is double the upstream depth. Anything less than that, and it may not be immediately clear whether a hydraulic jump is happening or if it's just random variation. But in a weak jump, it becomes more apparent. And you can see the flow patterns here, which become important because occasionally there are flow patterns which are very disruptive to the channel. And in an oscillating jump, when hydraulic designers are intentionally hoping for a hydraulic jump to occur in a certain place, they'll avoid this oscillating jump because it's not stable. Just the typical flow patterns that set up, some of these arrows are pointed downward. And what that means is that there's going to be an additional shear force than there normally would be on the bottom of the channel. And so that can contribute to scour, the wearing of concrete cladding. And so it's considered destructive, and it's generally avoided. And even if you have concrete cladding on the bottom of the channel, it's not always typical to have it on the sides. And so if you had a naturally lined channel on the side banks, then that could be scoured because of the undulation and the oscillation and so much turbulence in the jump itself. But if you design it so that the Froude number is between 4.5 and 9, that's kind of the sweet spot. The stable jump pattern, you'll notice that in these arrows, they're not pointing down, so it's going to avoid some of the scour that otherwise would occur. You have a nice big difference between the upstream and downstream depth. So the downstream depth may be between 6 and 12 times deeper than the upstream depth was. And because of that big change in depth, it's going to dissipate a lot of energy. You can crank up the Froude number a bit further, and then the rough jump is going to have quite a lot of energy dissipation. And because the flow upstream, for a Froude number of greater than 1, there's going to be such a high velocity before the jump that they would need pretty sophisticated stilling basins. They may need to even be injecting air underneath the water to provide like a cushion. That's a technique that they'll sometimes use in the penstock of a dam to ensure that there isn't cavitation that could cause some pitting and erosion of the concrete. They inject a thin cushion of air underneath the water when the velocities are really high. So strong and rough jumps are pretty uncommon and avoided where possible. There are a number of empirical approaches that have been used to estimate the length of a hydraulic jump, and our book presents 3 of them. One of the ideas is that the Bureau of Reclamation, which is kind of equivalent to the Army Corps of Engineers out west, in the western United States, it's generally the Bureau of Reclamation that operates dams and irrigation and so on. They've got a lot of expertise related to hydraulic design, the same way that the Corps of Engineers does. They have published a nomograph that if you know the Froude number before the jump, then that allows you to classify the jump type in the same way that we've just seen in the previous slides. And so, the oscillating jump, the stable jump, the weak jump is before oscillating, and so on. So this figure allows you to classify it based on the upstream Froude number, but then what it also does is you go up and you intercept the curve, and you go to the vertical axis, and then what this will tell you is the ratio between the jump length and the downstream depth after the hydraulic jump. So if we had, say, for example, about 2.5 for the Froude number, then we'd intersect the curve, go over to the left, and then that tells us that L sub j divided by y2 is 5. And so if you wanted to know the jump length, L sub j would be 5 times the depth downstream. So if you have 1 meter is the depth after the hydraulic jump, then that is telling you that the length of the jump from the beginning of the rollers to where the flow becomes basically uniform again would be 5 meters in length. So 5 times the depth. Now this is a little bit of an art, and it's very subjective, looking at the water and trying to decide where has the hydraulic jump finished. So you'll see that when we go down to the lab, that there is some uncertainty to how long the jump is, but what they're assuming in this case, in this illustration, is that it's back to uniform flow, where it's just Manning's equation predicting the depth. Yes?
So the length of the jump, the beginning of the length is defined at the highest point?
The beginning is defined at just before you start to see the turbulence. Yeah, so that starting point is where we've got supercritical flow, and now all of a sudden the depth is rapidly increasing. So that's the starting point to measure the length. And then the end is where you'd match back up with the normal depth that's defined by the tailwater characteristics. The length of the rollers, L sub r, means the rollers, and that's where you're actually seeing air entrained into the water, rather than just the gradual increase in depth that's after the rollers. The length in the rollers is maybe between 0.4 times the length of the jump, so 40% of the jump length if you have a relatively low Froude number. If you have a higher Froude number, then that could be 7/10 of the overall jump length. That's just kind of a rule of thumb, empirically observed. ratio of the roller length to the jump length. So if you wanted to incorporate these calculations into a spreadsheet, then it would be a challenge to do that with a nomograph, because in a nomograph you're kind of manually eyeballing where one of the intercepts matches up with another axis. So instead of just relying on a nomograph, the book also presents the ENGR jump equation, which predicts the jump length on the same factors, the Froude number and the upstream depth prior to the jump. And so you could draw a curve and see how well the two match up. The book even goes so far as simplifying things even further, and it identifies another jump length equation, didn't even bother naming it. That's how little they think of that other jump length equation, and they just say, it's usually, you have some A factor between 5 and 6.9, and then it's the difference between the depths. So if we have enough time to actually take some measurements of the jumps today rather than just observing the qualitative behavior, so if we can get quantitative about it, let's see if we can agree on the length of the jump, the length of the rollers, and see whether these equations have some accuracy to them. All right, so to get some practice doing those calculations before we get down to the lab, why don't you calculate the hydraulic jump length for the following scenario. What we know is the water going through the channel at a known velocity and a known width, and we know the depth upstream of the hydraulic jump. And so with that, you can calculate the Froude number, and this water velocity, that's upstream of the jump. The water flows at a velocity and the width of the channel, so all of those flow characteristics are at location 1. So practice calculating the depth after the jump, so use the Bellinger momentum equation for that, and then predict the length of the jump using all three methods, the nomograph, the ENGR method, and another method. So we've got V1, the velocity upstream, we got the channel width, the depth, so you can find A1, V1 is given, that gives you the flow rate Q. So if you know Q, then you can use this Froude number equation, and T, remember, means top width, and since this is a rectangular channel, the top width is the same as the bottom width, and that's just 0.25 meters. So you can find the Froude number, and then with the Froude number, you can use the Bellinger momentum equation to find the depth after the hydraulic jump. Okay, so let's just make sure we're on the same page with the Froude number and the upstream depth. So the Froude number, 5.05. Did anybody else get that same value for the Froude number? Okay, good. So that means that our downstream depth after the hydraulic jump will be about 0.666 meters. And, okay, so now the three methods that we're going to use is, number one, with the Froude number upstream of 5.05. So you go up on this figure. Let me see if we can get some maximum accuracy. So 5.05, we go up and then over. So I said that's about 6.1. So 6.1 is the ratio of the length of the jump and the depth y2. So L sub j is going to be 6.1 times y2, right? Yeah, so that's one of the methods using the nomograph. The other method, the ENGR equation. Now, on the Casio calculator, how do you do tan H? Is there a button on there that allows you to do that? Hyperbolic button? All right. So hyperbolic tangent. Okay. So according to the nomograph method, that predicts that the jump length is going to be 4.06 meters. And the Hager equation is suggesting that it might be a little bit longer, 4.96 meters. And then this other jump equation presented by the book, where it's just, if I took the middle value, you know, like it says that A may be between 5.0 and 6.9. So if I say, well, let's use 5.5, then that would give a jump length of 3.1 meters. The first two definitely seem more scientific, don't they? But I don't know, it's good just to see what's what all the different models are predicting. That's kind of sometimes with things with uncertainty like hurricanes or climate science, they'll develop a lot of different models, like 20 something, and then they'll show you like what do each of the different models predict so that you get an idea of the envelope of the uncertainty. You know, maybe the range is between, it could be as short as 3.1 meters and as long as 4.96 meters, but we have pretty good confidence that it's somewhere in those bounds. All right. Are there any questions on the jump length example? All right, we're going to skip over the slide that's in your notes having to do with jump profile. That's just an empirical method of describing the curvature of the hydraulic jump. Instead, let's just go straight to talking about gates. And a gate may be as simple as just a metal plate in a frame that has a handle on it. Sometimes it's just like bent rebar that's welded to the plate. And this is the kind of gate that a farmer would use to control irrigation into a field. And the higher you open the gate, the more water it allows out from the canal into the field. Sometimes they get a little bit more sophisticated, and one of the projects that I worked on when I was a practicing engineer before going back to work on my PhD was sizing and specifying some gates for a pretty large irrigation network. And these massive gates can get to be thousands of pounds, so that hand crank to open it is kind of just like a laughable backup, and really what you need is a really strong motor to lift the gate up. And when they get that large, the other issue is that the hydraulic pressure pressing them up against the frame is enough that the friction inside of the frame is a really important issue of how easily it can be lifted. So the force that you require to open the gate isn't just the weight of the gate, but it's also related to how hard the water is pushing up against the frame. Gates like this are used both in irrigation applications, but also they're used a lot in water and wastewater treatment, just to regulate flow in and out of stilling basins, aeration basins, flow equalization basins, disinfection tanks, and so on. So it's pretty important to be able to predict the flow performance through a gate. Here's a picture of a radial gate, and an advantage of a radial gate compared to a gate that's in a frame is that as the water level rises in a radial gate, that doesn't make it harder to open. Whereas in a gate in a frame, the deeper the water, the harder it is to open because of the hydraulic force that's pinning the gate up against the frame itself. In the case of a radial gate, you can't quite exactly see it, but the radial gate just rotates. I think I maybe have a side view in a minute. It rotates about a central point, and so that the water level, all of the forces are pushing in towards that central point, and it doesn't create any kind of a moment that's pinning the gate closed. But as the water level goes up, so does the flow rate through the gate. And you'll notice that this is a rectangular channel that the gate is placed into. So in its simplest, you can use the energy equation to predict the flow under a gate like this. There are losses that we'll account for with a coefficient But the energy equation is a starting point for understanding what's happening. And I've mentioned before that when you put an obstruction into a channel, that the water will pool upstream of that obstruction until there's enough energy that it achieves equilibrium again. And it's that unsteady condition that's the most interesting. I hope we get down into the lab so that we can observe, like when you first turn on the bench and the water level is starting to rise upstream of the gate, it's not quite in equilibrium yet. The flow that's approaching the gate is greater than the flow that's going out under the gate. But then as the depth increases, so does the velocity of the discharge. Because if the depth is getting deeper, then there's more pressure pushing the water through that opening. And so that increased pressure leads to a higher velocity, and finally, Q equals VA in will equal the Q equals VA out. Most rectangular gates most gate openings are rectangular, so that allows us to simplify the analysis of a gate a little bit. We can talk in terms of flow per unit width in a case like that. Now, there is some energy loss as the water goes through a gate because of turbulence inside of the water. And so that energy loss, one of the ways that it's manifest is with the contraction that occurs even after the water is past the gate. It's continuing to accelerate a little bit. So you'll notice here in this sketch, it's saying the gate is open a certain height. Here in this figure, it's labeled Y sub G. I think in subsequent slides, you're going to see it labeled with a W. That just means how wide open the gate is. But the depth is getting even more shallow. That contraction keeps occurring until finally it stops contracting, and then that's what we call the Y2, the depth that's downstream of the gate opening. And so that coefficient of contraction is pretty significant. What that means, 0.59 to 0.62, it means that if the gate was open 1 foot, that the depth would continue contracting until it gets to about 0.59 or 0.62 feet. Now, this is the scenario for predicting the depth upstream and downstream of the gate that we'd use if there was no energy loss. There is energy loss, and we'll talk about how to account for that. Here's the side view of the radial gate that I was talking about. You can kind of get a sense for if the forces are at every point tangent to the shape of the gate, so they're always pointing towards that central point of rotation, then that makes it so that really you're only lifting up the weight of the gate rather than the weight of the gate and the friction forces as well. The nice thing about underflow gates, as opposed to a broad-crested weir or as opposed to even a sharp-crested weir, is because there's underflow, then it doesn't trap debris and sediment that otherwise would be clogging the upstream part of the apparatus. So the velocity is increasing as you come to this obstruction, so the water is going very fast under the gate, and that just allows any kind of gravel or sediment that would accumulate to flow right through. So the orifice equation that we apply for the gate is that the upstream depth dictates the velocity under the gate. You remember that the orifice equation that we saw in fluid mechanics is that velocity is the square root of 2gh. And when we did that orifice equation, what we were usually measuring was to the center of the opening. It's customary here to just measure the entire upstream depth. So the upstream depth is one of the components of the flow rate through the gate. B is the width of the gate opening, which oftentimes is equivalent to the width of the channel. And then the coefficient of discharge is the fraction of energy that's lost as the water is approaching this obstruction. And a typical C sub C, coefficient of contraction, is 0.61. And so you can calculate the coefficient of discharge as a function of the coefficient of contraction and the upstream and downstream depth. So the coefficient of discharge varies depending on how deep the water is. Okay, so let's get some experience using the gate equations. What if we have a canal that's 4.5 meters wide, the Y1 upstream depth is 2.7 meters, but the gate is only 1.5 meters of the 4.3 meter wide canal. So what that means is that the B that you're using in this example is going to be different than the channel width. The gate opening W is 0.45 meters, and then after contracting, the downstream depth Y2 is 0.275 meters. So as described, let's calculate what's the flow rate through the gate. So your steps here is going to be to calculate the coefficient of contraction, C sub C, then calculate the coefficient of discharge, and finally to calculate the flow rate Q. So C sub C, C sub D, and then Q. Okay, so we know the upstream depth, how high the gate opening is. The width of the gate opening is just that, 1.5 meter width. And then we also know the downstream depth after the water has finished contracting. So the coefficient of contraction is 0.6111. Coefficient of discharge 0.5822, and then when we put all of that into the equation for the flow rate, it should be 2.86 cubic meters per second. Any questions about how to calculate flow with an underflow gate? Now, it's particularly appropriate that we talk about gates and hydraulic jumps in the same lecture, because you remember when we started talking about hydraulic jumps, I showed you some pictures of what can cause a hydraulic jump. Sometimes it would be when you have a supercritical slope matching up with a subcritical slope, and it has to go through the transition of supercritical flow to subcritical flow. And anytime there's a transition from super to sub, it has to go through rapidly varying flow. You can't have gradually varying flow connecting the two. But another example of something that will cause a hydraulic jump is an underflow gate. And so if we were to calculate the critical depth for this channel, and if the gate is below the critical depth line, usually what we would do in a situation like this is we would draw like a dashed line to represent what depth is associated with the critical depth. So if this gate is below the critical depth, then what that tells us is it's forcing the water to flow at a supercritical depth. And if it's flowing at a supercritical depth on a slope that can't support supercritical flow, then it's going to experience a hydraulic jump. So here you can see a picture of a gate that's doing just that same thing. It's causing a hydraulic jump because the gate opening is below the critical depth line. How you open the gate is another factor that can control where the hydraulic jump occurs. Last time I mentioned that the slope of the channel is one factor that can account for where the hydraulic jump is, because the slope of the channel is going to determine the normal depth downstream of the jump that the hydraulic jump is going to have to match up to. But the other factor that controls when and where the hydraulic jump occurs is the upstream depth. And so this gate opening and closing is going to change the Y1. So to determine whether or not the gate is going to cause the hydraulic jump to drown, there's a procedure here. We're going to go through this procedure in the second gate example for today. What we're going to do in that example is, first of all, find out, based on the downstream flow characteristics, what's the normal depth. So we're going to say that normal depth downstream is Y2. And then we'll calculate the critical depth to see whether or not a hydraulic jump can be supported. And by supported, what I mean is you can't have a subcritical depth if the channel is too steep, or if the Y2 is greater than the critical depth, then that means there will be a hydraulic jump that can be supported. All right, now problems like this often ask, how high could the gate be opened? You know, if you open that more and more, what it's doing is it's going to be getting the hydraulic jump closer to the gate. Because if I close this down more, then what that's going to have is a smaller Y1, and it will have to jump up at a deeper Y2. So as you pinch the gate closed, it pushes the hydraulic jump away from the gate. But as you open the gate, that draws the hydraulic jump towards the gate. And so in the analysis, they'll often ask, what's the maximum gate opening that you could have without drowning the hydraulic jump? And so what you do is you use the hydraulic jump equation, and you try and find out if your Y1 is going to be matching up with Y2, meaning the normal depth, and that's the perfect ideal case, is that the hydraulic jump immediately goes to the normal depth downstream. So then what you'd do is you'd solve for Y1, where Y2 is the normal depth, and then once you know Y1 and the coefficient of contraction, you can calculate W. So again, you get the Y2 from Manning's equation, the critical depth from just the channel characteristics and the flow rate. Then you would get the Y1 from the Bellinger momentum equation, and finally you'd calculate the gate height just as the ratio of Y1 and the coefficient of contraction. And as you close the gate, that pushes the jump. They call it running away from the gate as the jump gets further away. And if you open it, then it will approach the gate. And if you open it too much, then you wouldn't see the hydraulic jump anymore, because then that would cause this case that we saw last time where the jump is drowning. And by the way, did everybody get my email about the corrections on these labels? And so it's, the book isn't correct in labeling that Y2 and Y'2. It should be Y'1 for each of those. So I sent you the email on the correction. You need to apply both to the notes and to the textbook. All right, so let's look at this second gate example. We're going to apply this procedure, and we're going to ask how much can you open the gate without drowning the hydraulic jump. And so your calculation process here is, first of all, from Manning's equation. So I've given you the N value, which is the roughness of the channel, you know, the slope of the channel and the Q. This is a rectangular channel. So use Manning's equation to calculate what is the depth, the Y after the jump. That's the normal depth. And then calculate the critical depth for the second phase and see if a hydraulic jump can be supported. So in other words, compare Y sub C and Yn. And then the third thing will be to calculate the maximum gate opening. Let me write that on the board just to give you some outline of what you're doing. So step one, find what in this figure is the Y after the jump. Y after jump with the P by Manning's equation. Okay. Step two, find critical depth, Y sub C, and we know that Y sub C for a rectangular channel is flow per unit width squared divided by G to the 1/3 power. And then compare y sub c to the y after jump. And the question we're asking is y sub after greater than yc. If yes, then jump can be supported. And then finally, in phase 3, you're going to find the y before the jump with Bellinger. Momentum equation for the hydraulic jump. Coefficient of contraction is y before divided by w, and then so w is y before divided by the coefficient of contraction. So just do this first bullet point, and then I'll illustrate how you can find the depth behind the gate. That's where we will use the definition of coefficient of discharge for that one. So the channel's 5 meters wide and it's rectangular, which means the area will just be 5 times the depth. The wetted perimeter is 5 on the bottom and then 2 times the depth on the sides. So the wetted perimeter is 5 plus 2y. And when you solve for the flow rate, you should get 1.78 meters. Did anybody else get that same value for the normal depth in the channel? Okay, good. So that's our normal depth, and what we want to ask is, downstream is it subcritical conditions? Because if it's not subcritical conditions downstream, then there's not going to be a hydraulic jump. We'll be really disappointed if there's no hydraulic jump, because they're fun to look at. So the critical depth, if we compare the flow per unit width and the g to the 1/3 power, the critical depth is 1.366. And so that means that the depth downstream is greater than the critical depth, and so therefore a hydraulic jump is supported. So if this gate goes down far enough, it's going to cause supercritical flow under the gate, and in the channel downstream is subcritical flow. And the only way to match the two is with the rapidly varying flow hydraulic jump in between. Okay, so I'll leave that on the screen for a moment if you need to review the normal depth and the critical depth. Now the third phase, you're using the momentum equation to find what is the depth before the jump. So if I go back here to the sketch in the problem, yeah, the y before the jump is what we want to know here. And so we have the y after the jump. The y after the jump is just the normal depth that we calculated. So y after 1.78, then that means that the y before is going to be 1.022. You'll notice that here I'm not using the Froude number, but I'm using this ratio of depths. That's another one of the another version of the momentum equation. If I show you that from last time, when I first introduced the momentum equation, I think I showed you that we've got these two options. We can use the Froude number at 1, or you can use the ratio of the critical depth and the upstream depth. to find the downstream. So then therefore, if you're solving for y1, let's see. If you're solving for y1 before the jump, then it's just simply the y after divided by 2, and then the ratio of yc and the y after. Okay, so before the hydraulic jump, we expect the depth would be 1.022 meters. And the last part is just to use the ratios. So the coefficient of contraction is 0.60 according to the problem statement. So the coefficient of contraction 0.60. So if we know the y before, that is going to be 60% of the gate opening height. So if the y after the contraction is the same as the depth before the jump, 1.022, then that means that the gate must be open 1.703 meters. Okay, any questions on this example so far? All right, the last thing that it's asking is what's the depth behind the gate? If the gate is open W, then the depth behind the gate, we know the flow rate because that was given when we were calculating the normal depth. We were given the flow rate was 25 cubic meters per second, and we can calculate the coefficient of discharge because we know the C sub C, and we know the downstream depth Y2, but we don't know Y1. And so this is going to be a little bit tricky because the unknown is going to be in a few different spots in the equation. The Y1, the upstream depth that we're trying to solve for, well, that plays into the coefficient of discharge, and then it's also in the orifice equation. You know, what we're saying in the orifice equation is that the flow rate through this opening is related to the velocity of the water that's exiting the gate. And so it's the cross-sectional area of the opening multiplied by the velocity of the water. And so the velocity of the water depends on the depth upstream. So we've got Y1 in 3 different spots, but luckily if we set it up in the solver to solve for the Y1, then we can get that the depth is 1.883 meters. Now, I think that you have a homework problem that has some of the similar questions, so you'll get another chance to practice this where you're not rushing through in quite the same way that we are right now, but it looks like we did save enough time that we can go down to the lab and observe the hydraulic jump. So before we split to go down there, any questions on this illustration? So what we're going to see in the lab is if we can make the jump run away from the gate by changing both how wide open the gate is and also the slope of the channel. Those are the 2 things we can affect to change where the jump sets up. So we'll make it run, and then we'll make the jump drown by both reducing the slope and also opening the gate a little bit more. Okay, so let's meet down in the hydraulics lab.